Hi everyone. Thank you guys so much for coming to today's session. So my name is Evelyn, and I'm a data scientist at BAM Elevate. And for this session today, I'll be discussing a case study where we fine-tune transformers for location resolution. So in terms of the agenda, I'll first set the stage by providing an overview of the project and lay out the problem statement. And I'll then talk about our solution and how it addressed the pain points that we were facing. And finally, I'll share some key takeaways from our endeavor. So before I dive into the actual project, just wanted to quickly introduce who we are to help you better understand why we got involved in the project in the first place. So Balyasny Asset Management is a multi-strategy hedge fund, and BAM Elevate is a team inside Balyasny that is executing our late-stage venture strategy. So our mandate is to invest in startups that are in tech-enabled sectors, including enterprise, fintech, and health tech. So as you can see on the slide here, we have some logos of some of the startups that we have currently invested in. So at BAM Elevate, we have a dedicated data science team that is driving value for our investment process. So specifically, on the back of our firm's centralized data platform, we have been able to build data products and machine learning models, not only for our team, but also for our portfolio companies. So the project that I'll be discussing more today was actually an engagement where we supported one of our portfolio companies. So this is a portfolio company that is providing an enterprise supply chain intelligence platform. And the problem that we were trying to tackle is how can we automatically extract locations from news articles? So this is one of the first necessary text preprocessing steps that the company needs to do to enable more relevant and timely risk alerts to be sent to their customers to allow them to mitigate their supply chain risk. So to put things into more perspective and make the use case more concrete, let's take the example of the Suez Canal being blocked. So we need to pinpoint this location so that our portfolio company can use that information to quickly identify any customers who have goods moving through here and might be impacted by the supply chain disruption, and the portfolio company can alert them accordingly. So being the data scientists that we are, the first thing we did after collecting our business requirements were formulating them into a data science problem. As I mentioned before, the solution should take in news articles as input. And since we're trying to extract locations from news articles, in the output, we need to have the names of the locations, the start and end index of where the location string began and ended in the document. And we also, as I mentioned, need to pinpoint the location as well. So instead of converting the text of the location into coordinates, which is supported by many geocoding services today, like OpenStreetMap and Google Geocoding API, we opted to link it to its entry in a geographical database called GeoNames. So the output should also return the GeoNames ID for the location as well. So the reason why we chose to link the location to an entry in GeoNames is because it enables access to more curated and structured data. So as you can see in the screenshot where we have a GeoNames record for San Francisco Airport, GeoNames provides not only the coordinates for that location, but also other metadata as well, such as the location's place inside the administrative hierarchy, its location size, if that's available, and the type of location it is, and more. So this can be useful for establishing the context for that location and also help the company build more relevant alerts. So to summarize, at a very high level, the requirements for our data science solution need to accomplish two things. So first, it needs to be able to identify any chunks in the document that contain mentions of locations. And secondly, it needs to be able to link the mention of this location to an correct entry in GeoNames. So if you're someone who is familiar with NLP, you might find that what we're trying to do here sounds exactly like entity linking, which is a foundational NLP task that plays an important role in text mining. And for those of you who are less familiar, entity linking is commonly defined as the task of linking entity mentions to their corresponding entries in knowledge bases. And so it's usually composed of two subtasks, namely name entity recognition, NER, and name entity disambiguation, NED. So the first step in entity linking is NER, and this identifies the entities of predefined categories in free text. So here I have some examples of where NER might be helpful. So in finance, a use case for NER might be tagging companies in financial documents like 10Ks and 10Qs. And in a healthcare setting, where NER might prove to be helpful, could be tagging names of drugs in clinical notes. And so following NER, we then apply NED to bridge the entity mentioned to the knowledge bases, which then enable access, as I mentioned, to vast amount of curated data. So continuing with the same examples, in finance, after we tag the company, we can use NED to link the company to their record in financial database to access financial identifiers like ISIN, CDOs, and Bloomberg tickers. And in the healthcare example, we might want to use NED to find the record for the drug that we had detected in the previous step to a drug database like Drug Bank to be able to retrieve more information about that drug. So without a doubt, entity linking is a crucial task in NLP and is useful across many domains because of its ability to transform unstructured text into structured knowledge. I just wanted to quickly call out two of the many applications that it supports, just to underscore how useful it is. So one such application is knowledge graph. So people have used entity linking to build out and to enrich knowledge graph. And another application is question answering or retrieval augmented generation. So you can use entity linking to be able to create more precise queries for answer retrieval. And before I move on, I just wanted to quickly say that for our project, which was focusing on location resolution, what we did was actually just one domain-specific use case of entity linking. But I would say kind of the underlying general kind of design pattern and approach to this problem can be scaled to other domains. So I hope what I will be sharing next will provide some useful insights. So without further ado, let's talk about the solution we implemented. So the solution first processes the input article by applying a location detection module, which performs the NER step, and this will output a list of the detected locations in machine-readable format. And this list is then fed into a location disambiguation module, which does the NED, and this then produces the final output that has the detected locations as well as their geonames information if they're available. And here I have an overview of the system architecture. So as you can see under the hood, we have a model for each module. And so in the next few slides, I will dig deeper into each module and talk about how we approached it in light of the pain points that we faced. So in the location detection module, as I mentioned, this is the step that does an NER. And initially, we had surveyed off-the-shelf NER taggers, especially the ones that are transformer-based, because these ones have been the state-of-the-art for a while, and they've exhibited great performance on standard data sets. However, what we found that was they were not very generalizable, as these models were trained using data sets that have been decades old. And in addition, because these taggers were trained on data that also have other entity types like persons and organizations, the taggers were optimized more for precision rather than recall. And so what this means that they tend to struggle with kind of identifying and rounding up all the locations within the text. And moreover, in our literature review, we also found that they underperform on narrow location types like airports and train stations. And this is problematic for our use case because these types of granular locations are more likely to appear in a supply chain context. So to address the pain point that I just outlined, we ended up annotating a custom training data set that's representative of the news articles that our tagger is expected to process, which would be supply chain related and then more recent. And in total, we manually annotated almost 2,000 locations in 250 articles. In addition to that, we also bootstrapped this custom data set with 5 other open source data sets that have location entities and annotated in news articles. This is so that we're able to just build a larger and more robust training corpus. As you can see in the data set statistics, compared to the training data that's been heavily used for off-the-shelf models, which is co-out 2003, our corpus has 2 times more location entities annotated. And now that we had a decent training corpus, the next thing which we needed to figure out was what models we should train it on. So LLMs like GPT-4 and Llama 2 at the time were promising viable options, but the downsides were that they were expensive, have higher latency, and their model architecture are not the best suited for any NER tasks. So as a result, we decided to fine-tune a pre-trained Roberta model, which is a bird-like model that's open source and has only 125 million parameters, which is a tiny, tiny fraction of the size of GPT-4. And overall, I think we were quite pleased with the results that we got after benchmarking it against one of the state-of-the-art NER taggers. As you can see, we had achieved a much higher F1 score than the off-the-shelf solution. This means that our tagger was good at identifying locations correctly, and more importantly, it does not miss that many, so it has a higher recall. And having a high recall model is important for us because in the real life kind of scenario, if a location that has supply chain disruption slips through the crack, an alert that should have been sent out to the customer would be missed, and this could potentially cause the customer financial losses. And on the right side, you can see we also have the breakdown of our model's performance by different location types. And it shows that we have beat the state-of-the-art by significant margin for different types of locations, especially for the narrower types of locations that we care about. So next, I'll talk about the location disambiguation module. So for this module, we started off also just reviewing what's available off the shelf. And we found that the existing anti-linking solutions that are built specifically for location resolution have been generally rule-based or machine learning-based, whereas this current state-of-the-art anti-linking system that is domain agnostic have kind of been leveraging transformers for a while. Despite this, we didn't want to use the domain agnostic anti-linking system right off the bat because they usually link to Wikipedia, which is known to have less coverage of locations than geonames. So as a result, we created a new transformer-based anti-linking system that links to geonames. So this is a basic diagram, so I'll try to unpack it as best as I can. So first, on the left is the original location detection module, which is the NER implementation. And so under the hood is the Roberta model that we had fine-tuned with our training corpus. And it outputs the text of the locations that were detected, as well as their contextual embeddings. And on the right, we have the components that perform the actual NAD step. So based on the text of the detected location, as you see on the top right, we have a candidate generation step to select the top 10 candidates top K candidates in geonames using keyword search. Afterwards, we apply a transformer-based classifier to basically re-rank this set of candidates. And this classifier evaluates the match between the candidate location and the detected location by producing a score that's based on the location type, the description, and prior slight population size, as well as other similarity features. And so the reason why this classifier is transformer space, as you can see, is because we're encoding the candidate location into latent vector representation using Roberta, so that we can use them to compute some of the scores with the embeddings that we get from the NER model. So in terms of the training, we trained the classifier by first pre-training on Wikipedia-derived data. So we built this training data set using a recent dump of Wikipedia and generated the labels based on the hyperlinks. We then fine-tuned the classifier using the same training corpus that we use for the NER model. And so after training and evaluating the location disambiguation module, we found that it was able to correctly link to geoname 76% of the time on our test data set. And in real life operations, perfect match is not always necessary as long as the link location falls within an acceptable distance range. So to that end, we also calculated the metric accuracy at 161 kilometer, which basically measures the number of accurate predictions within 161 kilometer of the true coordinates. And for this metric, unsurprisingly, we got a higher accuracy of 86%. And finally, we benchmark our anti-linking solution end-to-end against the state-of-the-art refined system, as well as a naive baseline, which is just taking the top candidate location from running keyword search. As you can see on the left table, our model is much more accurate than our naive baseline. which just means that the transformer-based classifier was a necessary step for re-ranking the set of candidates. Moreover, our model had achieved a higher accuracy than the refined model, and is also 3 times faster in terms of inference speed. So this shows that tailoring, at least in our case, I think tailoring our solution to a specialized database is more effective than using a generic database. And finally, across most location types, our system also achieved higher recall, indicating that it's able to round up the correct geonames entry for locations in the article. So in terms of the business outcome, our protocol is now working on integrating the system into their platform for product enhancement, specifically enhancing their signal and event tracking capabilities by locations. And they're also looking to apply our approach and learnings to other use cases like company resolution. So now I will wrap up and share some of the key takeaways from our experience, and hopefully it will resonate with those of you who are or who will be working, who want to work on something similar. So the first one is a bit cliche, but I would say don't reinvent the wheel unless you have to. So I say really really evaluate your use case and see if there are already kind of off-the-shelf models you can use. As far as anti-linking is concerned, there are already several models that do really well out of the box. It has robust performance for linking to Wikipedia, and maybe that's sufficient for your use case. And I think for us, we had dedicated time to literature review, and I think it did pay off, and it saved us from doing unnecessary work. And for us, it was through kind of literature review that we had a better understanding of what the pain points that people who are in this field have elucidated, and it also helped us justify the lift of training our own models. I think the next point I wanted to say is that I think, in my opinion, like fine-tuning custom models for anti-linking can be helpful and can be an option you can consider when it's a very narrow domain-specific application. So from our experience, we found that fine-tuning smaller LLM can yield performance that are also pretty decent. And compared to prompting, I think it's just easier to tailor your models to evaluate them, and obviously it's more cost-effective. And it's another takeaway I think that belongs to this bucket is that sometimes the juice lies in the data rather than the actual model architecture. So be, I think, really thoughtful about curating your training data if you're going the fine-tuning route. So even though it might be a higher lift, if you have the resources, I would highly recommend collecting high-quality annotations for your target tasks. And if that's not possible, and you're still running into data scarcity, try bootstrapping with open source data sets you can find that could be tangentially related. And also, you can also consider synthetically generating your data. And so in our case, we had used the Wikipedia-derived data to supplement our training corpus and allow the NAD model to pick up general skills, even though when that corpus is out of domain. And the second takeaway is on the model architecture side, I think, especially if you're processing longer documents, I think any mechanism that can leverage your context can be helpful. And for us, it was as simple as computing the cosine similarity between the contextual embeddings of the candidate location as well as the locations that's been mentioned in the NAD classifier. And I think that helped to achieve a better performance. And finally, just on the deployment side, I would suggest housing a model behind a REST endpoint. It's not groundbreaking, especially for those of you who are like engineers and ML ops, but I think it's a good reminder for data scientists like me. And also, as you saw in the performance metrics, the model is not perfect by any means. And this is kind of expected because anti-linking is a very challenging task. And so when you're considering deploying this into production, I think it's important to work with your business stakeholder to understand the tolerance for error and implement the correct proper guardrails. So that could be setting error thresholds, having an ensemble system, or having a human in the loop to mitigate those risks. And so with that, thank you guys so much for listening, and I'm happy to take any questions you have.